Okay, guys, welcome. So today we're going to talk about the solution to a second order non-homogeneous linear ODE by using what's called the variation of parameters method. So now, so far we've talked about how we can solve one of these non-homogeneous second order linear ODEs as long as this R of X is a specific kind of function, right? So we've looked at if it was like e to the kx. We've looked at if it was like k times x to the whatever, j or whatever. And we've looked at like sines and cosines. Right, so that's sort of what we've done so far. Now, we would like to do, something that's a little bit more general, right? What if R of X is not one of these simple functions? What can we do to solve it? And that's going to lead us into what's called the method of variation of parameters, right? So basically, so we're going to do an example, but it's important to note here that you can get a particular solution of this form here. And of course, W is the Wronskian here, right? So it's the derivative or the determinant of this 2x2 matrix, right? And of course, Y1 and Y2 will be formed by a basis of solutions for the homogeneous version, right? Okay. So, and of course, this assumes that your ODE is in this form, right? So if you had something in front of Y double prime, you would want to first divide through by that. Now, if you can avoid this method, it's usually desirable to do so, because sometimes this integration, you can imagine, might get cumbersome, right? So the integration, depending on how messy your input function R is, you could have some messy integration to deal with. So if you can avoid using this method and thus avoid using the integration, that's usually recommended. All right, but we're going to look at an example where you don't have a choice but to use this method, right? So now we have a reciprocal of a cosine or a secant function, which it's not in our table of functions that we can use the method of undetermined coefficients for. So we need another way. Now, if you look at the homogeneous version that we've done a bunch of times now, y double prime plus y equals 0, we've shown that we have a basis of solutions that's given by cosine plus sine. And of course, if you find that Wronskian, you get cosine squared plus sine squared is equal to 1. All right. Now, that's going to be nice here because our particular solution has the Wronskian in the denominator. But in this case, if your Wronskian is 1, you're not going to really see it. Right. So now we just plug in everything that we have. Right. So y1 was cosine. So that's where this is coming from. And then y2 was sine. So that's where this is coming from. And your R term was secant, so that's where this is coming from. And of course, Wronskian 1, so you're not seeing that in the denominator. And then we get something similar in this second term here. Now, if we simplify, of course, negative cosine times sine of x secant of x will become negative cosine times an integral of a tangent, right? Now, if you aren't familiar with how to integrate tangent, the hint here is to use substitution. And you want to write that as sine over cosine. And then you can derive what that integral of tangent would have to be. But anyway, in the next integral, the cosine and the secant are reciprocal, so they are going to cancel, and you're just left with the integral of dx. So then you can get that the particular solution here is going to be cosine x times ln of cosine of x plus x times sine of x. Right? So then, of course, you would get that the so you get, sorry, so you would get that the general solution, of course, is given by the homogeneous version, which is, it looks like they reversed it here, right? So it would look like something, I guess they didn't reverse it, but they sort of combined it, right? So your homogeneous solution is coming from these two, and your particular solution is coming from these two. Right, and then you get sort of this funky looking graph here for that, right? So of course, if you had initial conditions, you could solve for C1 and C2, and of course you could do that if you were given those initial conditions. All right, so, and again, we're going to go through the methodology for this, but the idea is that this would be how you can answer a non-homogeneous second order linear ODE where that R of X is more general than stuff that we've already looked at. So this is sort of how this comes about, right? So you're going to start with a general solution of the homogeneous ODE. And we're going to assume now that C1 is some function of X, which we're going to call U of X, and C2 is some function of X, which we're going to call V of X. So the idea is that you're going to find U and V such that your particular solution is of this form. Of course, for the non-homogeneous ODE, right? So what we're going to do is we're going to look at equation 5 here, and we're going to substitute its derivatives into our ODE. Now, of course, you are going to need some product rule in here, right? So if you take the derivative of y sub p, right, you're going to get these two are resulting from the product rule of u y1, and these two are resulting from the product rule of v y2. Now, it can be shown that u prime times y1 plus v prime times y2, or in other words, these two terms equals 0, right? And we're going to use that a little bit later, so I'm just going to call that equation 6. So if they equal 0, then what does that mean? That means that these two terms are gone, and you just get y prime of y sub p prime is equal to u y1 prime plus v y2 prime, which is going to make taking the second derivative a little bit easier, because now we get this for our second derivative, right? So now if we plug each of these into our ODE, we're going to get something that looks like this, right? And we can shuffle some things around to sort of make it look this way. Now, again, the nice thing here is that since y1 is the solution of the homogeneous ODE, we know that that's equal to 0. y2 is also a solution of the homogeneous ODE, so that's equal to 0. So these two things drop out, and we're now left with u prime times y1 plus v prime times y2 is equal to r. Now, we also said earlier that equation 6, that we also know that u prime y1 plus v prime y2 is equal to 0. So now we have a system that we can solve using elimination, right? So it can be shown that we get u prime of w is equal to negative y2 times r, and then we can also show by elimination that v prime of w is equal to y1 times r, right? So since y1 and y2 are a basis, we can't have that w is equal to 0. Otherwise, our two solutions would be multiples of each other, and they would not form a basis, right? So that allows us to conclude that w is non-zero, which allows us to divide W, the Wronskian, over to the other side, right? So I should maybe make a note here that W is the Wronskian. And of course, to get U and V explicitly, we just need to integrate both sides. And of course, that's what's giving us what we had before, right? So the goal was to represent Y sub P as U times Y1 plus V times Y2, which we are able to solve for U and V. So plugging them in gives us what we had earlier. And again, just a reminder, you don't have to do this derivation every time. Just simply know that if you have a non-homogeneous ODE, right, where your R of X isn't something that's, nice and easy anymore, now you just apply this formula and you can get what your solution would have to look like. Okay, so that wraps up this video on the method of variation of parameters. So I will see you next time. I hope you enjoyed, and I will see you next time.